Hi everyone. This video is about growth models. We have two different models here. One is a linear growth model. One is exponential growth model. So we look at this one by one. The first video is about linear growth model. So we have two objectives. First, we want to learn the structure of these growth models. After we understand that, we want to apply it, being able to identify and then apply the correct model to solve application problems. So the first one, linear growth model. So we are going to derive this model or develop this model from a specific example. This example is from your textbook. So let's look at it. Marco is a collector of antique soda bottles. His collection currently contains 437 bottles. Every year, he budgets enough money to buy 32 new bottles. In other words, his total collection will increase by 32 bottles per year. Can we determine how many bottles he will have in 5 years and how long it will take him for his collection to reach 1,000 bottles? First of all, this is not a hard problem. Even if you don't learn any modeling, you can still figure it out. Just take a little bit of time to see what's going on, then you will be figuring it out. The thing is, in the real life, a lot of problems are way more complex than this. We do need a model. That's why we learn this modeling so that we can solve a problem in a systematic way. Okay, first of all, this 437 is the initial number, the total collection he has currently, and then year after year, his collection is going to increase by 32 bottles. So let's see how we develop this. We start with the initial value, 437 bottles. In modeling, we use the P0 to represent initial value. So we have this P0 equals 437 bottles. Now let's look at the several years numbers to see how we can develop the model. So after 1 year, that's year one, that's year zero. Year zero, that means starting value, that's year one, 1 year after. So we will have 437 plus 32, right? Each year he will buy 32 new bottles. So that's the total number after the first year. And everybody can add this together, so that's not our point. We want to develop a pattern, a formula. Now, another year passed, so we have 437 plus 32. That's previous year's number. Now we add another 32. In other words, we have 232 now. After 2 years, we have 232 because each year he will buy 32 bottles. That makes sense. So, but I'm going to rewrite this into a more compact way. So 437 plus, now we have a 232s now. 32 times 2. 232s now. Again, we don't do calculation. And third year will be, so previous year's number, which is 437 plus 32 times 2, that's the previous year's number, and plus another 32. So this year he will buy another 32. So 2 32s plus another 32, now 3 32s. 437 plus 3 32s now. Now we can continue write this, but now I think by now you may realize what's happening. So the number, if you look at this number, this is 1, you have 132. If this is 2, you have 2 32s. If this is 3, you have 3 32s. So these numbers are always the same, and that's the pattern. This is 0, you have 0 32, still consistent. So in other words, I can write this formula for any year. Say, for example, n years has passed. How many bottles he will have by that time? So 437 plus n32s. See? Depends on how many years has passed. So that's the called pattern. And from here, we can answer the questions actually. Now let's look at the question. Can we determine how many bottles he will have in 5 years? The n equal to 5 now, because it's after 1 year, after 2 years, after 3 years, after n years, after 5 years. So that means P5 equals 437 plus 32 times 5. Now let's do the calculation. 32 times 5, 160. So 437 plus 160. And this is the 597 bottles after 5 years. 597. So that's not hard. Now let's answer the last question. How long it will take for his collection to reach 1,000? 1,000 is total bottles. That's equivalent to this number on the left-hand side. This is total number. So total number is 1,000. And we need to figure out how many years. We don't know how many years. That's our n. We need to figure out this n. After how many years? After 1 year, 2 years, 3 years, n years. We need to figure out the n. So plug in this formula with these numbers, just leave this n as n so that we can solve it. Each year, the collection will increase by 32. After n years, it will reach this number. We just need to solve for n. So let's do the calculation. Move this to the left-hand side. So 1,000 minus 437 equals 32n. That's going to be 563. And equals 32n. So all we need is divided by 32 on both sides. So let's do the calculation. 563 divided by 32. 17.59. 17.59. So anywhere between, this is in years. So between 17 and 18 years, around that time, he will have 1,000 bottles. Now, let's look at this closer so that we can derive that model. This is just to identify a pattern to solve this particular problem. Now, let's see how can we enhance this so that it become a fixed model for similar problems. So for example, this guy started with 437 bottles. He could start with 500. He could start with 20. He could start with any number of bottles, is that right? So this is just the initial value. Usually we use this P0 to represent the initial value. In other words, in this formula, we derived for this particular problem right here, we can replace 437 with P0 so that we can generally represent the initial value. And this Pn still stay as Pn because it's a future value after n years has passed. And what is 32? 32 is how many bottles he will buy each year. That means that's increased amount each year. This is the fixed number for this particular problem. But he could have about 50 bottles per year instead of 32, is that right? Now this could be a different number. So we need another variable to represent this increase rate. This is like how many bottles increase or decrease if you sell bottles. But this is a change, it's a rate of change. We need a number to represent that. We need a variable to represent that. So in the book, they use D. D means it's called a common difference. It's increase, decrease amount. So replace this by D, replace it by P0, we get a new model. Oh, here it is. This is from the textbook. So future value equals initial value plus common difference, which is the rate of change or increase rate, increase, decrease rate. This is a certain amount. This is input represent time in this case. Again, I'm going to write it down here. Pn represent future value. P0 is the initial value. And D is called common difference. And it represents, you can also call it growth rate. Growth or decay rate. If it's decreasing, it's decay. But this is a certain amount, it's not a percentage, okay? N is just input. No input, no output, right? This is the output, this is the input. Now, how do we know a model is a linear model? That's a critical question, right? We are learning these two models. One is called linear, one is called exponential. How do we know if it is linear or if it is an exponential model? Linear characteristic of a linear growth model is that the increase or decrease amount is constant amount. It's not a percentage, it's constant amount. Like this guy, he will buy 32 bottles per year. So each year, his total collection will increase by 32 bottles. 32 is a constant number for him. If each year he will buy, say, 50 bottles, then that number is 50. But again, it's going to be an amount. It's not a percentage. So put it together. If the change is a constant amount, no matter increase or decrease, that's characteristic of being a linear model. So try to remember that. That makes it very easy for you to identify if you have a linear model or not. So this number is a growth rate. In terms of amount, this is the initial value. In other words, for any growth model, if you look at it from common sense point of view, if you want to have growth, you have to have a starting point to grow, right? And besides starting point, you have to know how fast it will grow or decay. So you have two components in the growth model, initial value and the growth rate. That's why we have this tool. After that, you just need to have input, output to have a model. Okay, let's see how we use this linear model. Again, whenever we have real life problem, you don't know. This is from linear modeling section. This is from exponential modeling section. We don't know that. We just have problem, right? So the key is that I want to identify what kind of model is more appropriate for this particular problem. Okay, now let's look at example 1. It says the population of elk in the national forest was measured to be 12,000 in 2003 and was measured again to be 15,000 in 2007. If the population continues to grow linearly, we are told growth is linear. At this rate means they won't change. And what will be the elk population in 2014? So this is the two numbers are in 2003 and 2007. We are asked to figure out the number in 2014. So we are calculating future value. We are calculating this. So that means we need to know all of other numbers. Since we already know this linear model because we are told so, so we write down the general formula directly. Pn equals P0 plus D times N. Now, in order to have a specific model, we have to have initial value and growth rate. Then we just plug in input to get output. Okay. Now, initial value, say we have 12,000 in 2003. You can use that as the initial value. Actually, you can also use 15,000 as the initial value. Later on, we address this issue, which one to use. Actually, it doesn't matter. And now, we also need to know the growth rate. We don't know the growth rate. We only know that in 2003, it was 12,000. 2007, that's 4 years after, 15,000. But apparently it's an increase from 12,000 to 15,000. When they say growth linearly, that means each year the amount of increase will be the same number. So we want to know how many elks increase in each year. So this increase amount is for 4 years. So we are going to use 15,000. This is going to be our D, the growth rate. 15,000 minus 12,000 divided by 4, because in between there are 4 years. So this is 3,000 divided by 4, 750. That means the elk population will increase by 750 per year. That's constant amount. That's our D. Initial value, as I said before, you can use 12,000, you can use 15,000. You may ask, how come you can use either one? The thing is, if you use 12,000, you're going to start counting your N start at 2003. But if you use 15,000, you're going to start counting your N from 2007. The result will be the same. That's why it doesn't matter. So let's use this number. So Pn equals P0, 12,000, plus Dn. D is 750 times N. N is the input. So this is the real model, particular model for this particular problem. After you set up the model, it's time to plug in numbers to calculate the result. Now we are asked to find out the population in 2014. Since we start counting this N, how many years, starting from this number, which is corresponding to 2003. So N is from 2003 to 2014. If you do subtraction, and that's 11 years. So plug in P, and this 11 years. This number always the same as this number. So P11 equals 12,000 plus 750 times 11. So let's do the calculation. So 12,000 plus 750 times 11. 20,250. 20,250. That's the population. Yeah. Okay, that's our first example. Basically, first, identify what model is appropriate. Then write down the general form of the model. Then always figure out what is the initial value, what is the growth rate. Then you have a particular model for that particular problem. Then you can plug in the input and get the output. Now let's look at another example here. And gasoline consumption in the U.S. has been increasing steadily. Consumption data from 1992 to 2004 is shown in this table. Find a model for this data and use it to predict assumption in 2016. Again, we are going to predict future value. If the trend continues, when will consumption reach 200 billion gallons? This is in billions. This is years, this is billion gallons. So again, whenever you have a new question, don't worry about what they ask you. Understand what's going on here first. So basically, we want to predict future value of gasoline consumption based on this table, based on this trend. In other words, we have to create a model to simulate this trend so that we can predict future. If you don't see any trend, how do you predict future? It has to be a trend. Now there's two possible models. At least within the scope of this book, this course, we only consider two models. One is a linear model, one is an exponential model. Now this time, we are not told whether it's linear or not. So that's out of the question. There's no way we can know that. Only thing we have is this table. In other words, we have to determine whether it's a linear or exponential from this table. How do you determine that? That's why we were given this in the book. I copied this from book, this whole problem. Now in the real life, all you need to do is get a graphing paper, or if you have Excel, you can use Excel, draw this table. This is like X, Y, X, Y, X, Y. Put them point together, look at this trend. It's almost a line. As long as it's close to a line, straight line, it's not like wave, that's a linear model. So in this case, we can say approximately this linear model. So after we determine this linear model, we're going to write down the general form of linear model, like what we did in the last example. So the general form is Pn equals P0 plus Dn. Now we just need to figure out the initial value and the growth rate. Now initial value, so we have so many numbers, which one is the initial value? In theory, you can pick any one of this. So I'm gonna pick the one of those the starting ones. So in the book, I don't know, I don't remember which one they use. It doesn't matter. So I'm gonna use the second one. You can use this one, this one, this one. Doesn't make much difference after you have a model. Now, after we have initial value, we have to know the growth rate. Apparently, it's growing, so this D is going to be positive. If it is declining, it's going to be negative. But apparently, this is positive. Look at this number, year after year, it's increasing. So growth is going to be a positive number. But how do we know which number to use? Now, here's something from pre-algebra. Basically, if you want to know the average growth rate, you need 2 data points to calculate that. In pre-algebra, this is how we do that. We have 2 data points, x1, y1, and x2, y2. This is only for linear growth model. So this is linear growth model. And in pre-algebra, we calculate slope of the line. And that slope of the line later on, we're going to talk about that. It's the same as this D, same as D. So we just borrow that formula. The formula says y2 minus y1, x2 minus x1. What does that mean? What that means is that this is the year, this is gasoline consumption. This is the year, this is gasoline consumption. We just need to pick 2 data points and plug in to get that growth rate. So I'm going to pick one. So the one I already picked the initial value. This is 1 data point. I'm going to pick another one. Maybe I use the last one, 2004. You can use this one. You can use this one as long as they're not too close. So I'm going to use this one. And this one is 2004, 136, 1993, 111. I'm going to write down these 2 data points. 1993. And that is 111, and in 2004, I will just copy that. That is 136. Now I'm ready to calculate the growth rate, average year after year. Now I don't know if you can make a connection between this one and the one we just finished for the elk population. Remember, they gave us 2 numbers. And one is 2003, we have 12,000. The other one, 2007, we have 15,000. What's the difference between that and that? No difference. In certain year, you have number, another year, another number, then you calculate the increase or decrease. So I'm going to do the calculation. Using y minus y, x minus x. Okay, it doesn't matter which one minus which, but y has to be on the top. So 111 minus 136, 1993. Minus 2004. So if you do this calculation, this is negative 25. And this one 7 years. 7 years is 11. So negative 11. So we just need to do calculation. And 25 divided by 11. We got 2.27. So about 2.27. So 2.27 average increase, 2.27 billion gallons. Average increase per year. So that's our D. Now we're going to plug in to get a specific model for this particular problem. Initial value, since I used this one to do calculation, I'm going to take this one. So 111, 111. So don't put the 1993 in here because we are talking about the consumption of gasoline. And this is the gasoline. And plus 2.27 times n. See, we have growth rate, we have initial value, this is input, this is output. Now it's time to answer questions. I didn't even read the question. Say, first, find we already have the model. When will the consumption reach 200 billion gallons? It's one. It's about the time. So which one we're looking for in this whole thing? We're looking for in how many years? And they ask us when, that is in which year. After we figure out how many years it takes to reach that 200 billion, we will figure out in what year. So let's look at it. This is 200 billion. And 111 plus 2.27 times n. So we just solve for n. 200 minus 111, move this to the other side, equals 2.27 n. So this is 89 equals 2.27 n. So we divide by 2.27 on both sides. 89 divided by 2.27, 39.2, about 39 years. Now, in which year they ask us when will reach 200 billion? We need to know that year, not how many years. This is why we need to know whenever you have initial value, you need to know what time is corresponding to. We use a 1993 number. That means starting with 1993, after 39 years, you reach 200 billion. So we just add 39 years, 39.2 years to 1993. This gives us 1. 1993, 39.2. This is 2, this is 3. About 2032. In year 2032, it will reach 200 billion gallons. And first of all, I want to make this clear. This is about the modeling. No model is exact. That's why when we use this data, you don't have to use a certain data point to make that model work. Model, the functional model is give you general direction, give you estimation. As long as your estimation is close enough, that's a good model. That's a good model. Okay, now let's do some connections between algebra and this linear model so that you have a broader understanding of this model. So the title is the connection between the linear model and the slope y-intercept form of linear from pre-algebra. Now that pre-algebra linear equation, it's in this format. They call it slope y-intercept form of linear equations, linear. So you have one variable on one side, the other variable on the other side. You have number in front of the other variable, you have constant number. Now, if we look at our linear model, Pn equals P0 plus Dn, you can write Pn equals Dn plus P0 and just switch this two. Doesn't make any difference in addition if you switch them, because 1 plus 2 equals 2 plus 1, right? So that you can easily compare. This our input, this our output, this is the input, this is the output. The number, there's number in front of input, there's number in front of input, there's constant number, there's constant number. In other words, these two have exactly same structure. Exactly same structure. So what's the significance? Significance is this. And in this slope of y-intercept form, the number in front of input is called a slope. In other words, the slope, when you draw a line, linear equation always have a graph of a straight line. So that line has a slope. The slope of the line is your growth rate. In other words, when you read a graph, they ask you, what is the growth rate? How do you read that from graph? If you know it's equivalent to the slope of the line, you just try to figure out the slope of the line. And that's your growth rate. So what is P0? P0 is equivalent to this. That's your initial value. So from the graph, what is the initial value? It's y-intercept. In other words, if you have graph, this is y-axis, this is x-axis, this y value, that's the initial value because it's intercept with y-axis. This line intercept with y-axis, that's the y-intercept, that's equivalent to this. That's why we need to make this connection, so that you can read this model from a graph, not just from description. Okay. It says through the comparison, m is the slope. It represents the rate of change. That's growth or decline, the rate of change. It is equivalent to d, so equivalent to our growth rate. Now b in the slope y-intercept model is equivalent to the initial value p0. So these two are equivalent. Now let's do some practice to identify the growth rate or declining rate or decay rate, and from these linear models. They just using different letters. If you replace this y with pn, replace x with n, that's a linear model. They are exactly the same thing, actually. So for each linear model, identify the average rate of change, which is growth rate, which is m, which is the slope. They're all the same thing, and the initial value. So if you look at this, compare this to y equals mx plus b, the number in front of x is average rate of change. That is equivalent to our d. So your answer is the average rate of change is 3. What does that mean? For every unit change in x, y will increase by 3 because it's positive number, it indicates increase. And the initial value for this one, initial value is equivalent to this b, which is this. That's constant number by itself. It's 1. That makes sense. What does that mean, initial value? When x equals 0. If x is 0, this is gone. Y equals 1. That's your initial value. Okay, second one, very similar. So our average change, average rate of change equals -4. Don't forget negative sign in front of it. So if you have an average rate of change is negative number, that means it's declining, it's decay rate. We don't call it growth rate anymore, it's decay rate. So that means for every unit increase in x, y will decrease by 4. Y will decrease by 4. That's the meaning of it. Input, output. Look at this in terms of input. Input changed by 1, output changed by -4. The change go in opposite direction. If x increased by 1, y decreased by 4. If x decreased by 1, y increased by 4. That's the meaning of negative sign, opposite direction. Okay, what is the initial value then? The one that is by itself, constant number is -1. It starts with -1. In other words, when x is 0, y equals -1. That's the initial value. Okay, and the next one are going to be some examples that is similar to the homework problem. So let's look at this one. And the growth, yeah, this is some refreshment. The growth or decay rate d in our linear model here is equivalent to the slope, or we call it rate of change, m, in the slope of y-intercept form of linear equation. It just say this growth rate equals slope in the linear model. The growth rate in your linear model is the same as the slope in the slope y-intercept form of linear equation. Now here's one of this. Say identify slope y-intercept from this graph. So how do you identify slope? Now slope, first of all, that's the calculation. y2 minus y1, x2 minus x1. In other words, you need 2 points. If you have 2 points, x1, y1, that's 1 point. x2, y2, that's 1 point. You plug in, you get a slope. So we just need to pick 2 points. I need 2 points. As long as these 2 points belong to this one, you will get the same slope. But since we need to read these numbers from this graph, we have to pick the point that we can read the exact number of them. Otherwise, you're going to have error. So the easiest one, this one, because this point is exactly on the line and exactly at a number here. It has another one. You can use this one. This is also exactly in the cross section. We can read this. This x is 3, this y is 400. This point is called point 2. Just pick some point that is easy for you to read. So I'm going to plug in up. I'm going to get these 2 points. This one is 0, 800. Make sure you don't write 600, 6 or 800. Each point is associated with 2 numbers. One is x value, one is y value. Since this point is on the y-axis, just like y, just like x, and x value going to be 0 automatically if it is on the y-axis. If it is on the x-axis, y going to be 0 automatically. So the other one is 6 and 0 for this one. Now we can calculate m. 800 minus 0, y minus y, x minus x, 0 minus 6. And when you do plug in numbers, make sure you do this in a consistent way. You see, 2 minus 1, 2 minus 1. So in other words, if you use the number on the top minus the number on the bottom, you have to do the same thing on the for the other variable. So what do we get? 800 over negative 6. And if you do calculation, let's do the division. 800 divided by 6. And the result is negative 133.33, negative 133.33, depending on how many decimal digits they require you and how work you round it appropriately. I just do the calculation without concerning that part. So you got negative slope. What does that mean, negative slope? When slope is negative, remember slope is equivalent to the growth rate. It means it's declining, it's decreasing. That's why this line from left to the right is decreasing. So slope is negative. So we get slope. What is the y-intercept? Remember y-intercept is point on y. So this y-intercept. So y-intercept, let's say y-intercept is 800. That's equivalent to this b. That's equivalent to the initial value p0. Okay. So what this means is that for every hour, the hour from left to the right increasing, every hour passed, this value, I don't know the unit, it didn't give us unit. The value on y-axis will decrease by 133.33 for every 1 hour passed. That's the meaning of that slope. Okay, we have another one. So there's 2 more examples for this video. Second one, this is the exact same graph, just different questions. So this distance from home. So this really represents distance from home. And this is the time in hours. According to the graph, this is the question. According to the graph, the average rate of change, aka slope, yes. So we need to fill in this blank to represent the slope. We just did that calculation, is that right? So I'm going to redo that. M equals 800 minus 0. So let's get this point 0, 800, 6, 0. That's the 2 points we used. So we just repeat that basically. 0 minus 6 is negative 133.33. So we just put it in here. And it's measured in. Now, this is just number. They ask you what is the average rate of change, which is this, and it's measured in. They want you to identify the unit of this average rate of change. How do you know that? It tells you already. I didn't write that. These 2 numbers are from y-axis. Y is in terms of mile. And these 2 numbers are from x-axis is in terms of hour. So mile on the top, hour on the bottom, what does that mean? It means miles per hour. So negative 133.33 miles per hour. That means whenever you have 1 hour passed, the distance to home will decrease by 133.33. In other words, this person is driving home from a place that is 800 miles away. Every 1 hour passed may not be driving because car cannot go this fast. Maybe it has been trained or something else. So every hour passed, the distance from home will be decreased by 133 miles. That means getting closer to home by 133 miles. Because this distance from home, this distance is decreasing, getting closer to home. So this measured in, your answer is miles per hour. That's your answer. And the last one, the cost in dollars of a gym membership for N months can be described by the explicit equation this. In other words, this equation, or you can say this model, represents the total cost of a gym membership for N months. In other words, if you keep that membership for N months, this is your cost, PN, and it's calculated using this, depending on how many months you want to keep that. So what does this equation tell us? So whenever you have such question, you need to identify the component of this. That means, I can answer this way because apparently this is in the form of linear model. If you compare that to the general form, P0 plus Dn, if you compare that, this is initial value, a number by itself, a number in front of n represents growth rate. So in other words, this is positive. That means your total cost of membership will increase if you use more and more months. And that's just common sense. The longer you use a gym, the more you need to pay. Okay, now this is called the initial value, but when you answer this question, you cannot answer initial value using that general word because it's about gym cost. So you have to talk about it using the specific scenario. So the initial cost, you don't say initial value. The initial cost, because this whole thing about cost, is $70. That means you don't have to use it, but you have to pay $70, like a starting fee, something like that, starting fee, and to get you started. Now, thereafter, each month you need to pay $30. That's why this is called growth rate. It grows with time. Each month you will, this is called rate of change. Each month you need to pay $30. So what does this mean? So $30 is monthly fee. And PN is the total cost. And this one, we already told this, you don't need to explain this. So again, after this a little bit analysis, everybody understands the meaning of this formula. Depending on how many months you're going to use the gym, plug in the number, you can calculate total cost. And that's the meaning of the initial setup value, setup cost. And after that, each month, you pay $30. Just like when you go through a toll bridge, and they have maybe a monthly pass, say it costs $20. After that, each time you use that bridge, you pay $1. If you don't have what is that? Pass, monthly, the pass, the $20 pass, maybe each time you have to pay $3. It's just different business model. Okay, this is the video for the linear model. The next video is about exponential model. So see you in the next video. Bye, everyone.